So first, for the 6 Henry inductor, the voltage for that one, positive on the left, minus on the right, is 6 di dt. 6 di dt. Okay. There's also a 2 Henry mutual inductance from the 10 Henry inductor. So the current goes into the positive, so it enters for the 10 Henry, and then it exits for the 8 Henry because it goes out of the inductor through the dot. So since the current enters for the 10 Henry, the induced voltage at the 6 should be positive at the dot. So this is going to be positive on the left, negative on the right, 2 di dt. Okay. Now, the 8 Henry, the current exits. That means it's a minus sign at the dot here for that mutually induced 4 Henry inductance. So this is going to be minus on the left, plus on the right, 4 di dt. Okay. What about the 8 Henry inductor? What's the voltage for the 8 Henry inductor? Not mutually induced. What's the voltage, the self-inductance? It's 8, but no negative, just 8, right? So it's positive on the left, negative on the right. That takes care of whatever signs, right? And it's 8 di dt. No. So current obeys passive sign convention, just like when we were in DC circuits. So if this is flowing left to right, my inductor's self-induced voltage follows the passive sign convention, current into the positive and out of the negative. So since you asked it, let's go ahead and do this one. So that means this one will be positive on the left, negative on the right, 10 di dt. Current into the positive and out of the negative, right? So now going back to the 8 Henry, the voltage induced from the 6, current goes in at the dot, so it should be positive at the dot. So that's going to be minus on the left, plus on the right, 4 di dt. I want to find the induced voltage from the 10 Henry. The current enters, so it's going to be positive at the dot on the 8 Henry. So that is also negative on the left, positive on the right, 5 di dt. Okay. Now we need to do the 10 Henry inductor. So this one would be the induced voltage from the 6. Current enters at the dot, so it's positive at the dot here. So that's positive on the left, negative on the right. What's the value? Positive on the left, negative on the right. What's the value? This is induced from the 6 Henry. It's 2 di dt, that's right. Last one is going to be the induced voltage from the 8 Henry. The current exits the inductor through the dot, so it's going to be negative at the dot here. So it's negative on the left, positive on the right. What's the value? 5 di dt. So now what we're going to do from left to right is add all of these up. So I'm going to have 6 plus 2 minus 4 plus 8 minus 4 minus 5 plus 10 plus 2 minus 5 di dt. I'm just adding them up from left to right. 6 plus 2 minus 4 plus 8 minus 4 minus 5 plus 10 plus 2 minus 5 di dt to get the total voltage. And that should be 10, I think. 10. Ten di dt. So the net total inductance is 10 Henry. Remember, we won't be doing differential equations in here, so you won't solve these until we start talking about phasor analysis. You will solve them in 205 using Laplace analysis, or if you take digital circuits using Z transforms, digital controls, okay? Questions?
So now let's do example 2. The first thing we're going to do is find the self-inductance for each inductor. So that's 10 di dt, 12 di dt, and 8 di dt. And please note that once again, we are assuming that the current flows from left to right. Now we're going to find the mutual inductance. So it's 6 di dt minus 6 di dt for the 12 Henry inductor for the mutual inductance from the 10 Henry and the 8 Henry. Next, we're going to find the mutual inductance for the 8 Henry. That's minus 4 di dt and minus 6 di dt. And then for the 10 Henry inductor, the mutual inductance is minus 4 di dt plus 6 di dt. And now we're going to add them all together. And you get that the net total inductance is 22 Henry. And the total voltage across the network would be 22 di dt.
Okay, so now let's see what this looks like in a circuit. Let's see what this looks like in a circuit. Like I said, we're just going to write the equations. We're not going to actually solve these. So I'm going to put some symbols here to make it easier for us to write the equation. So I'm just going to call this IS of t and VS of t. And let's see if I can do this without writing the dependent sources now and you understand what I'm doing, okay? So I'm going to call this clockwise current I1 of t and this clockwise current I2 of t. And I'm going to use the mesh current method in order to solve. So I'm going to do KVL at mesh 1 and KVL at mesh 2. So KVL at mesh 1, starting with the 4 ohm resistor, is going to be 4 times I1 minus IS. Starting with the 4 ohm resistor, 4 times I1 minus IS. The self-induced voltage for the 2 Henry inductor is 2 di1 dt. The mutually induced voltage from the other 2 Henry inductor, current enters at both inductors, so it's going to be positive at the dot, and it's going to be 8 Henry, so the mutually induced voltage is going to be 8 d what? di2 dt. Very good. This is the self. This is the mutual. And now the voltage across the cap is going to be an integral. It's going to be 1 over 0.2, the integral, from T naught to T of, since the capacitor is shared between 2 meshes, it's going to be I1 of tau minus I2 of tau d tau. The voltage across the cap is going to be an integral. It's 1 over the capacitance, the integral of the current. Since it's shared between two meshes, it's I1 minus I2. And set it equal to 0. Are there questions about that? Okay. KVL at mesh 2. I'm going to start with the capacitor again. It's going to be 1 over 0.2, the integral from T naught to T. When I taught this to my students in DC circuits, we always assume the mesh we're on, all the passive elements assume the passive sign convention. Obey it. I know some people don't teach it like that, but I do, to be consistent. So when I'm on mesh 2, this now becomes I2 of tau minus I1 of tau d tau. You still get the right answer by doing this. It's a way to be consistent. That's the voltage across the cap. The voltage across the inductor is 2 di2 dt. That's the self-induced voltage. The mutually induced voltage is going to be positive 8 what? di1 dt. The voltage across the 8 ohm resistor is going to be 8 I2. And then we'll just put plus Vs of t for the voltage source. And set that equal to 0. Okay, example 4. Okay? So I can now have one where they're mutually induced, but it's not a touching, so it's just two separate loops. And I'm going to define that first one as a clockwise current I1 of t, and the second one as a clockwise current I2 of t. If you're having problems understanding the mutually induced, you can keep putting the dependent sources, right? I just figure once you understand, I don't do that anymore, but you can keep putting the dependent sources if you want, right? So I'm going to call this Vs of t. Let me do one with dependent sources so I can show you what I mean. So here's Vs of t. And I just put a dependent source in series with my inductor that's going to represent the induced voltage like that. And then same over here, where I put a dependent source to represent the induced voltage. And so here is 4 ohms, 1 over 8 farads, 2 Henry. There's the 1 Henry mutual inductance, 1 Henry here, right? So it's the same circuit. I just put dependent sources in series with the inductors, and I put the voltages on those to help you to remember. That's the difference between the one I just did and this one, right? So if this is I1 of t, and this is I2 of t, I now look at, let's say, I2 of t, and I see that it enters the 1 Henry inductor at the dot. So the induced voltage over here is going to be positive at the dot. So that's positive at the bottom, negative on top. Okay. Over here, I see that the current exits at the dot. That means that it's going to be negative at the dot over here. So it's going to be negative on the bottom, positive on top. So that means the voltage here is going to be the 1 Henry mutual inductance di2 dt. So this is going to be just 1 di2 dt. So mutual inductance and the current over here. There's no shared meshes this time, so we don't have to worry about shared current. Okay. And over here, The mutual inductance is still 1, but the current is I1. So this is going to be 1 di1 dt. 1 di1 dt. Now what we need to do is write the equations. KVL at mesh 1. I am going to do, starting with the 4 ohm, 4I1 plus 8, the integral from T naught to T, I1 of tau d tau, that's for the capacitor, plus the self-induced voltage 2 di1 dt, minus di2 dt, and that equals my voltage rise, or equals Vs. 4I1 plus 8, the integral I1 of tau d tau, plus 2 di1 dt, minus di2 dt equals Vs. Okay, KVL at mesh 2. I'm going to start with the 2 again. So it's going to be 2 I2 minus di1 dt plus the self-induced voltage di2 dt. Okay, so once again, this is the mutual and this is the self. Up here, this is the mutual and this is the self.
All right, now let's try example 5. So KVL at mesh 1 is going to be VG equals R1 I1 plus L1 di1 dt minus di2 dt. That's the self-inductance and the mutual inductance. And KVL at mesh 2 is going to be L2 di2 dt minus M di1 dt plus R2 I2, and that's equal to 0.
All right, example 6. Last one for today. Last one before we move on to the next topic, I should say. So we have 3 meshes here. But remember, when you have a current source, we don't do KVL. So we don't write a KVL equation for that bottom left mesh, because the whole point of mesh current method is to find unknown mesh currents, and I know that mesh current is IG, so I don't write one. So I only have to do KVL at mesh 1 and mesh 2. I only have to do KVL at mesh 1 and mesh 2. Okay, so let's do KVL at mesh 1. Starting with the 20 ohm resistor, it's going to be 20 times I1 minus I2 plus 20 times I1 minus I2. The 5 ohm resistor is going to be 5 times I1 minus IG. Okay. The self-induced voltage for the 4 Henry inductor is going to be plus 4 di1 dt. Okay, so now what goes on here at the bottom? I have a dot at the top of the 16 Henry. I can either define it as entering or exiting, all depending upon whether I do IG minus I2 or I2 minus IG. I like entering, so I will define this current going down And that current going down is IG minus I2. So if that current enters, it's positive at the dot here, and this becomes plus 8, the derivative of IG minus I2. Let me do that again. This inductor is shared between two meshes. So I can say that the current flowing through it is either IG minus I2 or I2 minus IG. Depending upon how I define it, that defines whether the current is entering or exiting that dot. So if I choose to use IG minus I2, the current enters that dot, which means the voltage should be positive at the 4 Henry. So it becomes positive 8, the mutual inductance, the derivative of IG minus I2. Everybody see that? Mathematically, if you choose the other direction, you'll still get the right answer. It's algebraically the same thing. To solve these in the time domain, we use differential equations. You would do a little bit of that in 205. And here, when you solve these, we're going to use phasor analysis, which means you're going to solve them in the frequency domain, which uses algebra and complex numbers. We will probably start talking about that tomorrow. You are going to solve them, but not in the time domain, because you have to have DE to solve them in the time domain. Here, you're just learning how to write the equations, because you're going to need that. All right, so KVL for mesh 2. KVL for mesh 2, we're going to start with the 20. Now that I'm on mesh 2, it's going to be 20 times I2 minus I1. The resistor is going to be 60 I2. The inductor is going to be the self-inductance 16, the derivative of I2 minus IG. The self-inductance is going to be 16 times the derivative of I2 minus IG. Everybody see that? The mutual inductance is going to be, the current enters at the dot, so it's positive at the dot here, so it's going to be a minus 8 times what? di1 dt, and we set that equal to 0.